Okay, hello everyone. I'm Andrea Sabatucci, a PhD student in Roma La Sapienza, under the supervision of Professor Omar Benar. And I'm here to present some of the results of a work that appeared today on the archive, made in collaboration with Omar Benar, Andrea Maselli, and Costantino Pacidio, about the possibility of inferring some information on the trinuclear interactions from astrophysical data. So, okay, in this presentation, I will report the details, as I said before, of the study aimed at inferring direct information on the trinuclear interaction directly from astrophysical data. What we have done is we are fixing a given microscopic model describing nuclear matter, which in this case is the dynamical model used to derive the well-known APR, equation of state. And then we have considered the coupling constant of the repulsive trinuclear interaction as a free parameter that we varied in a small range between its around its correct assumed value. And then we have generated a set of APR-like equation of state by varying this parameter, and then we have performed Bayesian inference on this parameter, employing the current value available astrophysical dataset, particularly with the observation of the GW 170817 and the observation of the two nicer pulsars. And finally, we extended this analysis to a set of simulated data that could be a set of simulated observations that could be performed by the future Einstein telescope in order to see what kind of improvements we will get with the third generation of gravitational wave detectors. So what is important is that in this study, we are taking a slightly different approach for what is usually done in this field, because we are not constraining the equation of state curve, but we are fixing a particular dynamical model. And then we are trying to make inference on a parameter which is directly related to the microscopic dynamics. So it's a sort of complementary way to employ astrophysical data to extract information. So this slide is unnecessary for the audience. Basically, all of us know that neutron stars provide a unique opportunity to investigate the properties of matter of cold and ultra dense nuclear matter. So I will go fast on the formalism of the APR equation of state. If you have any question, I can ask you later. But in this formalism, the nuclear matter is thought is described in the framework of nuclear many-body theory, which is thought as an infinite system of point-like nucleons interacting by means of two nucleon and a trinucleons interaction. And at this point, when you write down an Hamiltonian, you have to choose your potential, and in the APR equation of state, they use the phenomenological argon D18 nuclear potential, which accounts for an accurate fit of the nuclear scattering data up to the energy lab, which is around 700 of MeV in the laboratory frame, which turns out to be can be related to densities of about 4 times the nuclear saturation density, which is the average central densities of neutron stars of around 1.4 solar masses. So it appears to be a good choice in order to describe the behavior of nuclear matter at the densities that are expected to be inside a neutron star. And then for the trinuclear interaction, they use the Urbana-9 potential, which I'm going to describe it on the next slide. And then once you have write down the Hamiltonian, you can derive the equation of state of cold nuclear matter by computing the ground state energy of your system, which is usually done, which is done in the case of the APR equation of state by employing a variational approach in which you define a correlated trial ground state, and then you minimize the ground state energy. And you have to use some of complicated techniques of nuclear many bodies, such as cluster expansion and Fermi-Abernethy chain resolution. Okay, so trinuclear interaction. Why do we have to consider trinuclear interactions to describe nucleons? Because nucleons aren't actually point-like particles, but they have an internal structure. So with trinuclear interactions, we account for the internal structure of nuclei. The Urbana-9 model, for example, can be divided in these two contributions, which is an attractive 2 pion exchange trinucleon potential that is described by the Feynman diagram that you can see here in this picture, in which a nucleon interacts with another nucleon and then excitate a delta resonance that then decay, emitting another pion which interacts with a third nucleon. And then a purely phenomenological or repulsive trinucleon interaction, which is an isoscalar contribution, who introduce these two terms introduce two coupling constants, two free parameters that are adjusted in order to reproduce some low density, so some saturation density properties, in particular the coupling constant of the attractive two-pion exchange potential is adjusted to reproduce the binding energy of 3 and 4 helium, and then the coupling constant of the repulsive trinucleon interaction is adjusted in order to reproduce the correct value of the nuclear saturation density, which is 0.16 femtometers at -3. So the repulsive term is purely phenomenological and only constrained at nuclear saturation density. So motivated by this, we have we wondered if it's possible to infer some information about the high density behavior of this repulsive trinuclear potential, since it's as already said, is constrained only at low densities, and moreover, if you look at the contribution at the energy of nuclear matter at the high density, this contribution becomes dominant. So we have reparameterized the ground state expectation value of this repulsive trinuclear interaction by placing a free parameter before it, and then we have varied it in the range between 0.7 and 2.0. With alpha equal 1, we recover the usual APR equation of state. And here we can see the mass radius diagram that are generated by this parameterization. So we can see that by small changing of these parameters, we explore a quite large set of the mass radius diagram within the same dynamical model. And here we can see the tidal deformabilities of a binary neutral star system together with the constraints imposed by the LIGO observation, by the LIGO Virgo observation of GW170817. So we can see already at this stage that there is a great sensitivity of neutral star observables to variations of this coupling constant. So at this point, we have try to make things more quantitative, and we have performed Bayesian inference, employing, as already said, the available astrophysical datasets. So we have used the gravitational wave observation of 17017, the observation of the Neisser pulsar PSR J0030. And finally, in these results I'm presenting here, I'm presenting the results in which the PSR J0740 was introduced only as a maximum mass constraint, because I'm presenting here the results of a previous paper in which we have not included there wasn't still the analysis of the radius constraints. In the paper that is that you can find today on the archive, we have extended this analysis also to also including the radius measurement of the PSR J0714, but the results slightly changed. So we have sampled the posterior distribution of the set of parameters that are the alpha parameter and the central pressures of the stars that was observed by means of a Markov chain Monte Carlo simulation employing an EMCEE algorithm. And so this is a slide which basically explaining how does a Markov chain Monte Carlo works. We have sampled alpha and the central pressure. Then we recovered the astrophysical parameter with the T of the equation, and then we decide to accept or reject the move by comparing by computing the posterior distribution. So here are the results for the marginal distribution of alpha with respect to the different data sets considered. Here we can see the Neisser results. Here the analysis performed only with the gravitational wave results, and these are the multi-messenger scenario. In all of these plots, we can see the results with and without the maximum mass constraints. The black line is the results with the maximum mass, the constraint on the maximum mass, and the green line is without imposing the constraint on the maximum mass. As we can see in this case, the single observation alone is still not accurate enough to have some relevant constraints on this parameter. In particular, the maximum mass constraints basically does all the job and is the main contribution that contribute to shape the posteriors in a marked way. So, and we can say that, however, there is somehow preference towards higher values of alpha, even if the original case of alpha equal 1, which recovered the APR equational state, is still largely compatible at 90–95% confidence level. Okay, so we have extended this study in order to start with a set of simulated data in order to study two scenarios, an increasing number of observations with the current detector networks at design sensitivity. In particular, we have sampled a set of 30 binary neutron star events with two different injected values of alpha, and we have tried to see if we can resolve between these two values of alpha with a set by combining up more observations for the case of the current detector. And then we have repeated this analysis with by generating observations that should be performed by the future Einstein telescope. These are the results for the Ligo Virgo detector network, and we can see that this is basically. These are the violin plotted. Here is the marginal posterior on alpha. And we can see that in most of cases, it's basically unconstrained. It is spread all over the range of all over the available range for alpha, with the exception for few observations, such as this one, which is peaked around the injected value, which is the dashed line, this one, and little others, which are a particular combination of a low chirp mass and an high signal to noise ratio, which is the best configuration to have a good accuracy. And here we can see the plot of the best scenario, which is this observation here. On the bottom axis, we have the chirp mass of the binaries, and on the top axis, we have the signal to noise ratio of the observation. And here is the posterior related to that event. And as we can see, we have the two cases for the two injected values of alpha equal 1.3 and alpha equal 1.0. And we can see that, however, we are unable to resolve with just one observation between these two scenarios. By combining up the best 6 observation with a signal to noise ratio, which is higher than 20, we can see that the pictures slightly change, in particular at 19% confidence level, which are these vertical dashed lines. We can exclude, for example, in the case of the observation related to the dataset with alpha equal 1, we can exclude the injected value of alpha equal 1.3, but still the picture does not improve in a very significant way. However, the picture slightly changed with the Einstein telescope observations, and we can see here that we can report on the same violin plot the results for both the two datasets that are generated with alpha equal 1 and alpha equal 1.3, and we can see that in most of the cases the posteriors are perfectly separated, and we can resolve between the two injected values of alpha also with just one observation. In particular, by combining, sorry, I've reported here, this is the best case, the best observation of the Einstein telescope, and we can see that the posteriors are very, very narrow and very well separated. And we can see here the worst case, the most overlapping posterior for the Einstein telescope. And here is a combination of the 6 worst events of the Einstein telescope, and we can see that even if we are unlucky, and we observe only events that are not very accurate, we can combine them, and combining them up, we can perfectly resolve between the two injected values of alpha. Finally, I have a picture which is useful to visualize the constraints that can be imposed on the mass radius diagram by constraining alpha. Here are the constraints from the actual astrophysical observations, and here are the constraints for the best event with the Einstein telescope. Okay, so by summing up, we have investigated the constraints that can be imposed on the trinuclear interaction by with the current and future astrophysical observations. We have seen that current measurements are still not enough accurate to have a strong impact on this kind of analysis. However, we have seen that with the upcoming third generation detector, the picture should improve in a very strong way. So we think that the future of this field is very bright. So thank you for the attention.
So questions, Jerome?
Very nice talk. Thank you very much. Excuse me. I have a question about the saturation density. You said that this parameter influenced a lot the saturation density. So do you have a PDF for the saturation density associated to this preferred model or to the distribution of alpha parameter?
Sorry, I don't have a PDF for the saturation density. However, I can comment about the fact that, as I said, changing the coupling constant of the trinuclear interaction will, since it's tuned to reproduce the saturation density, obviously will change a little the value of the predicted saturation density, and we have limited the range of alpha between 0.7 to 2.0 because we have at most a discrepancy of the 15% of the nuclear saturation density, which turns to a discrepancy of the 3% on the binding energy of symmetric nuclear matter. Maybe I have a backup slide. Don't know, here. So we have, this is the alpha equal 2, which is the most the deviation for the correct value of nuclear saturation density. And here we have the alpha equal 0.8. Here is the expression of the saturation of the nuclear density with respect to nuclear saturation density. However, this is a very brutal approximation for the trinuclear interaction, but we are interested on the high density behavior of the trinuclear interaction. So maybe we can find out, once we have an information about how stiff should be the equational state and how the nuclear interaction should behave at high density, maybe we can try to improve a model for since it's phenomenological, to take into account the correct value for the nuclear saturation density by changing the high density behavior. So it's a way to have some information on what we are missing, because as I said, for the nuclear interaction, we have the scattering experiments. So it is reliable to high densities, but with trinuclear interactions, we have no empirical information. So this is a work in this kind of direction.